My dear students, welcome to my class. Today we are moving to discuss on the topic resonance effect. My class is mainly focusing on the syllabus of plus 1, plus 2, degree and post graduation. So you can utilize this class. Okay. So before moving to the concept, let us consider an example. This is a clock where three hands are there: second hand, hour hand, and a minute hand. We cannot predict the position of these three hands at a particular point because it is continuously moving, right? We cannot predict the position here, whether it is here, because it is continuously moving. All the hands are continuously moving, right? Similarly, in organic chemistry, we cannot predict the behavior of certain compounds by using a single structure. The behavior can be explained with the support of a state of hybrid or an amalgamated structure or a combination of two or more structures. This phenomenon is called resonance. This is the definition in plus 1 plus 2 base. So let me repeat. The behavior of certain compounds in organic chemistry cannot be represented by using a single structure. It can be represented by using a hybrid structure or a combination of two or more structures. This is called resonance. And why this is happening? What is the reason behind by representing more than two structures? Let's move on to the concept then. And before understanding the concept, we must know certain terms in that is continuously using in studying this resonance effect. That is one of the main term is pi bond. As you all know that a pi bond, in a double bond, one is a sigma bond and one is a pi bond. So in a double bond, this is sigma and this is usually pi bond. In a triple bond, this is sigma and these both two are pi bond. We can predict either of one is a sigma bond, okay, and the two others are pi bond. This is a triple bond case, okay. And pi bonds, how they are forming? The overlap of p orbitals, right? The overlap of p orbitals is the reason behind the formation of pi bonds. A basic concept, that's all. So, and this is one important thing in understanding the resonance. The second is conjugated system. What is a conjugated system? Conjugated system is nothing but in organic chemistry, in a compound where single and double bonds in alternative position. See, single and double bonds. See, let's consider this example. This is double bond is there and a single is there in alternative position. This is an example of this chain, this carbon compound, an organic compound is an example of a conjugated system. Let's consider another example. An allyl group CH2 double bond CH single bond CH3. Okay, this is a single bond and this is a double bond. Double bond and single bond in alternative position. It is called a conjugated system. Okay, very important example. Benzene. See, this is a pi bond and this is a pi bond and this is also a pi bond. So three pi bonds are there. So in this class, we consider pi bond is equivalent to pi electrons. Okay, pi bond is equivalent to pi electrons. This pi can be represented by either using this Greek word pi or pi. Okay, I use this Greek word for simplicity. Okay, so pi bonds are represented in this resonance class. Pi bonds are equal to pi electrons. So just like the clock structure, let's consider the benzene structure. The benzene structure, the ring structure of benzene is discovered by Octet Kekule. You all know that he is a chemist, an organic chemist. In his dream, he discovered the structure of benzene. These are the two alternative structure of benzene. Okay, these are the two alternative structure discovered by Kekule. Kekule. He is the organic chemist who discovered the structure of benzene. And the high reactivity of benzene. Benzene is discovered by Michael Faraday, but the structure is determined by Kekule. Okay, remember that. The high reactivity of benzene is mainly due to resonance. And the reason behind is the pi bonds, but pi electrons inside it. The pi electrons are delocalized. What is delocalized? Free to move. It is continuously moving. The pi bonds are continuously moving. So that's the reason why here the pi bonds are between, let's consider 1, 2, 3, 4, 5, and 6. 6 carbon atoms are there. The 1, 2 carbon, 1, 2, there's a double bond present between 1 and 2, which comes between 1 and 6. Right? 1, 2, 3, 4, 5, 6. 6. Because the pi bonds are continuously moving, the pi electrons are continuously moving. That is known as delocalization. 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 Delocalization of pi electrons. The delocalization of pi electron is the important factor behind resonance. Okay, so the delocalization of pi electron is the important factor behind resonance. So let's consider this. These are the two resonance structures of benzene. I will detail in next chapter. These are the two structures that is discovered by Kekule towards the benzene ring, and this is the hybrid structure. Hybrid structure or amalgamated structure of benzene, because the pi electrons are continuously moving. This is what represented by pi electrons are continuously moving. Why it is continuously moving? Because it is not localized. It is free from the limitations of localized. So it is delocalized. It is continuously moving. So this is the hybrid structure, and these two are known as resonating structure or canonical structures. Okay. Let us consider another example. This is a conjugated system with a pi bond is there. A conjugated system with a pi bond and a sigma bond is there. And this carbon, the terminal carbon is carrying a vacant orbital, right? It's a carbocation, a vacant orbital, right? An allyl carbocation. Allyl group is that allyl carbocation. The terminal carbon is having vacant orbital. So what happened? The delocalization of pi electron will happen. So the pi electrons, the pi bond will shift towards here. The shift towards the vacant orbital. As a result of that, what will happen? This carbon will carry, see, this carbon will carry, the first carbon will carry positive charge and a double bond. The vacant orbital will get filled by the pi electrons and a double bond will come there. A double bond will come there. Okay. So these two are the resonating structure or canonical structure or resonance structure of allyl carbocation. And this is the plus and plus. This is the hybrid structure. Hybrid structure of allyl carbocation. Okay, so you understand the concept, right? So just like a clock where the hands are continuously moving, the pi electrons are delocalized, which is continuously moving in a conjugated system. A conjugated system is a compound where single and double bonds are in alternative position. Okay, so we consider one of the main important example is benzene, where the pi bonds are continuously moving, and in a conjugated system like allyl carbocation, where the pi bond is shifted towards the vacant orbital carrying a carbocation, carrying a carbon carrying a positive charge, and forming a hybrid structure. So this is an example of resonance in the case of benzene. So you can see that this is the benzene structure, and pi bond is there. Okay, pi bond is there. The delocalization is happened on benzene ring. That is, delocalization is means the pi electrons are free to move inside the ring. So what happened? This pi bond is shift towards this corner carbon atom, and the negative charge is coming. Okay, and this negative charge is moving to 1, 2, 3, 4, 5, and 6 carbon atoms that are there. Between 2 and 3 carbon atoms. Okay, and the 3 and 4 pi bond, the pi bond between 3 and 4 will move into the fourth carbon atom, the para position. So negative charges comes there, the pi electrons will come there, and again the pi electrons are delocalized, moving to the between 4 and 5, 4 and 5, and the pi bond between 5 and 6 moving to the sixth carbon atom. So negative charge will come to the sixth position. So the pi bonds, alternatively pi bonds are forming. Okay, and finally the last structure is coming. So these two structures, the first and the second, this last one, these two structures are called Kekule structure of benzene. Okay, Kekule structure, and we can represent it as simply what is this dotted line, dotted circle represent? This is called delocalization. Delocalization of pi electrons in benzene. These structures, these structures are called, therefore, these structures are called resonating structure. What is called? Resonating structure. Resonating structure or canonical. Canonical structure or resonance structure. Okay, these structures are called, the combination of more than two structures are called resonance structure or canonical structure or resonating structure. And but we can simply represent that compound into another structure, a state of having lowest energy, which is called hybrid structure. This is the hybrid structure of benzene ring, and this is the canonical structure. And the first one and the second, the last structure is called Kekule structure. Okay, so what is the difference between this hybrid and this resonating structure? This hybrid structure, why it is representing? The hybrid structure is having lowest energy. Okay, so lowest energy is for hybrid structure. Hence, this structure is a very stable structure for the benzene. And there is one more important factor is there. The difference between the energy of hybrid structure and the most stable canonical structure. There are these main structures are there in the case of benzene. The difference between the energies of hybrid structure and the most stable canonical structure. The most stable means a most lowest energy. Can structure is known as resonance energy or resonance stabilization energy, RE. That is called resonance energy or resonance stabilization energy. What is this? The difference between or the difference between hybrid and the canonical structures. The difference in between the energies of hybrid and most stable canonical structure of a compound is called resonance energy or resonance stabilization energy. Why it is very important? If the resonance energy is more, if the resonance energy is more, greater will be the stability of that compound. If the resonance energy is very high, the stability, the stability of the compound is also very high. This is very important. Okay, resonance energy is more, stability also more. Second point. Okay, very important. If the resonance energy is more, stability also high, right? Similarly, number of resonant structures high, stability also of the compound is also high. If the number of resonating structure is high, stability of that particular compound is also high, right? These are the two important points you should remember in solving many questions. Okay, resonance energy is high, stability also high. Greater the resonance energy, greater will be the stability. More the number of resonating structure, more will be the resonance energy, more will be the stability. Okay. So we move on to the second part, conditions to affect resonance phenomena. The first and foremost condition is pi bonds. Pi bonds in alternative positions. Pi bonds in alternative positions. The very simple example is we have already illustrated it is in the previous part, benzene. So here benzene ring, here one pi bond is there and a single bond is there. Again pi bond is there and a single bond is there. Again pi bond is there. So pi bonds are in alternative position. What will going to happen? This pi bond is shift to this terminal carbon. Okay, and as a result of that, a benzene ring with a negative charge here is come to, and this negative charge, that pi electrons come to the terminal, the second carbon, the first carbon. First, 2, 3, 4, and 5, 6. The second carbon will move to the adjacent bond, and this pi bond is moving to the terminal. What will going to happen? Negative charge will comes here, double bond will comes in this position, and this negative charge is comes to here, and this double bond comes to this terminal carbon. What will going to happen? Double bond comes to here, double bond already there, and negative charge is here. And finally, what will going to happen? This negative charge comes here, and a double bond comes here. Okay, so pi bonds in alternative position enable the resonance effect smoothly. This is the first and foremost condition. Okay, and the second condition. Okay, you should remember this because in MCQ questions we must have to understand all these conditions, whether resonance is possible in the given objective type question, given compounds or not. Second is pi bond and lone pair, lone pair of electrons in alternative position. Pi bond, pi bond and lone pair of electron. Let's consider a very important simple example. CH2 double bond, CH single bond, NH2. This is an amino group attached to a vinyl group or an ethene. Okay, here nitrogen is carrying lone pair of electrons and a pi bond. So this is an example. A pi bond and a lone pair of electrons in alternating position. What will going to happen? This will come to here and this pi electrons will come to here. Okay. This lone pair will comes to here and pi bond comes to here. So the resonance structure will become CH2 minus CH double bond NH2 plus. Okay. So this is the resonating structure. What will happen? The lone pair will move towards the conjugated system. Here you should remember an important point. Please note this down. The lone pair electrons is very free to move than a pi electron because the pi electrons are bonded, but the lone pair is very easy to move. Okay, so lone pair readily move than that of a pi electron. So the lone pair carried by the nitrogen atom is readily available towards the conjugated system. So as a result of that, the pi bond will move towards the terminal carbon atom and forming a canonical structure. As a result of that, the negative charge is carried by the terminal carbon atom and the positive charge is carried by the nitrogen atom. Also, this carbon, this negative charge is moved to the here and this will move to here. Similarly, forming what will going to happen? CH2 double bond CH single bond NH2. Okay. So these are the canonical structure of uh, an example of an organic compound where pi bond and lone pair of electrons in alternating position. The third condition is pi bond and negative charge in alternative position. Okay, pi bond and negative charge in alternative position. Let us consider an example of allyl carbanium. Here, CH3, CH2, sorry, double bond CH, CH2. So this is a pi bond and this is a anion. This is called allyl carbon. Okay, allyl carbon. Resonance is possible in this structure. This carbanion, the negative charge comes here and this pi bond comes here. What will going to happen? CH2 minus CH double bond CH. Okay. Similarly, what will going to happen? This charge will comes here and this will comes here. So the same structure will repeat. CH2 double bond CH single bond CH2. So we can say that the canonical structure we can these are the canonical structures and we can say the hybrid structure is minus minus. This is the hybrid structure. Fourth condition is a pi bond and a positive charge. Pi bond and a positive charge. Let's consider an allyl carbocation. Positive charge is there. Okay. What will going to happen? This is the pi bond. This pi electrons will shift here. Right? So a double bond comes here and a positive charge comes to the terminal carbon. Okay. And the next canonical structure is what will going to happen? This will come here and similarly the positive charge comes here and a double bond comes here. So resonance is possible here. And what is the hybrid structure then? the hybrid structure will become CH2, CH, CH2. Positive and positive. This is the hybrid structure. Okay, this is the hybrid structure of allyl carbon atom. So the fourth condition is a pi bond and positive charge in alternative position. The fifth condition is pi bond and a free radical or odd electron or free radical. What an odd electron in alternative position. Let's consider an allyl free radical CH2 double bond CH2. Okay, this is an odd electron. So what will going to happen? This is a pi bond. So a pi bond with an odd electron in alternative position here and here. So not a complete arrow, a half arrow is there. Okay, the head of the half arrow. So what will going to happen? One electron comes here and CH2, an odd electron, CH double bond CH2. Right? And again, what are going to happen? This will come here and this will come here. Okay, CH2 double bond CH2 and an odd electron will come here. These are the canonical structure of allyl radical. Allyl free radical. Allyl free radical group, and the hybrid structure will be CH2 single bond CH2 dot and dot. This is the hybrid structure of allyl free radicals. Okay. The sixth condition is when a lone pair, okay, a lone pair of electron and a positive charge in alternative position. Let us consider this example. CH2, this is an ether group. Okay, so the terminal carbon is carrying positive charge and a lone pair is carried by the oxygen. So what will going to happen? This lone pair will comes to here and CH2 double bond oxygen is become positive charge and CH3. Okay, so this is the sixth condition where resonance can be possible. So there is another important fact to note that this carbon is not completed the octet rule postulated by the scientist Louis Octet. According to Louis Octet rule, the carbon means any atom in a compound must complete its octet. So in this case, the octet of this carbon is 6. When this lone pair comes to here, now the octet is completed. Okay, here octet is only 6. Here octet is 8. What is octet rule? The number of electrons in its valence shell must be 8. Okay, any atoms in a compound, the number of electrons must be 8. In the valence shell must be 8. That is the octet rule. So when a lone pair and a positive charge in alternative position, resonance is possible. Okay, so we have discussed the conditions, 6 conditions. First one is pi bond in alternative position, for example, a benzene ring, and a pi bond and a lone pair of electrons in alternative position. We have taken an example of an amino group attached to a vinyl or a double bond conjugated system. The third is a pi bond and positive charge in alternative position. We have considered the example of allyl carbocation. For this, a pi bond and a negative charge in alternative position. We have considered the example of allyl carbanion. Fifth condition, a pi bond and the odd electron in alternative position. We have considered the example of allyl free radical. The sixth condition is a lone pair and positive charge in alternative position. So in this kind of examples, we must note whether the all atoms in that compound completed is obeying Lewis octet rule. What is known as Lewis octet? So we will discuss about this Lewis octet rule in the next part of the resonance effect. Now we move on to the third part of the resonance class, rules for validating resonance. If you are provided with a compound, we have to use these rules for whether to check that compound is possible for resonance or not. Okay. The first and foremost rule is all participating atoms in a resonance must be coplanar, which is essential for the better overlap of p orbital and delocalization of pi electrons. Let us consider an example of benzene itself. So this is benzene, right? This is benzene. We can write it as a coplanar shape. Okay. So these double bonds are represented by p orbitals, right? So p orbital, as you all know that p orbital is in a dumbbell shape. So all six carbon atoms and nitrogen atoms are on the coplanar. Okay. So which is essential for the overlap. The overlap between the p orbital is essential for the formation of pi bond, and which is in turn very important for the delocalization of pi electrons, and these are the main rules for validating resonance. So the overlap of p orbitals create pi bond, and hence the delocalization of pi electrons will become more easy. So resonance is possible. So this is one illustration of the first rule using penicillin. Okay. The second rule is position of all atoms must be same in all the resonating structure. Okay. In a resonating structures, canonical structures, all atoms must be in the same position, provided the position of lone pair, pi bond, or pi electrons, odd electrons, free radical, positive charge, negative charge can vary. But the position of atom must not vary in all the resonating structure. Let us consider an example. See, this is a chlorine attached to a conjugated system. The chlorine is having lone pair. So lone pair in alternative to double bond, which is resonance is possible. What is the resonance structure there? This lone pair will comes here and the double bond will goes to here. So Cl get a positive charge and lone pair is there. A double bond between chlorine and carbon, and a single bond between CH2 and a negative charge on it. Right? See, the position of lone pair vary. The lone pair will comes to the terminal carbon, and the double bond comes between Cl and CH. But the position of atoms didn't change. So that is the second rule. Position of atoms must be same in all the resonating structure. Let's consider another example. Here, it is an allyl free radical. So, this an odd electron is there. So, the first one, the pi bonds is split up into, and the resonating structure will become CH2, free radical comes here, CH, double bond CH2. Okay. Here, the position of free radical and the pi bond change, but the positions of atoms must be same. So this is the second rule. In this case, we must remember another question-based answer. Tautomerism. What is the difference between tautomerism and resonance? That's one of the main important point should be noted when we discussing the second rule of resonance. Okay. Tautomerism is nothing but in organic chemistry, certain compounds which exist in interconvertible structures. Okay, a single compound which exists in interconvertible structures, which is mainly due to the positions of the rearrangement in the position of hydrogen atom. Let's consider this example. This is a ketone. Okay, whether resonance is possible in this case or no, that's a kind of questions we'll ask. Okay, here this CH3, where one of the hydrogen atom will remove from this position and reoriented into, okay, reoriented into an alcohol. The ketone will reorient into alcohol. This kind of structural isomerism is known as tautomerism, but this is not a resonance. Okay, this is not a resonance. We cannot call a tautomer as a tautomerism or tautomer will obey a resonance rule because the positions of all atoms must be same in all resonating structure. Here the position of atoms are changing. Okay, so tautomerism cannot be considered as a resonance favorable compound. The third rule of resonance effect, which is all resonating structure must obey Lewis Octet rule. What is this Lewis Octet rule? Lewis Octet rule says that all the atoms in a compound, or in our case, all atoms in a resonating structure must possess 8 electrons in its valence shell. Okay, 8 electrons in its valence shell. That is the postulate of Lewis Octet rule. So let us consider this example. This compound resonance is possible because lone pair is there in alternative to double bond. So suppose this pi electrons is moved here. Okay, what will be the chance? CH2 plus CH double bond NH2. Okay, is this compound is exist? Does this case is possible or not? No, because the octet of this carbon atom is fails. The octet rule, this carbon, the terminal carbon fails to obey Lewis octet rule. See that there are not 8 electrons in the valence shell of carbon atom. So this is not possible. This case is not possible. So what will be the resonating structure? The actual resonating structure will be this lone pair will comes here and this double bond, the pi electron will come to the terminal carbon. So the actual resonating structure will be okay. So all resonating structure must follow Lewis octet rule. That is the third rule of resonance. Fourth rule of resonance says that negative charge should be preferably reside on more electronegative atom. This is a special rule. So this rule can be applied to identify major or minor product using resonance. So the negative charge on a compound which obeys resonance, the negative charge on a compound preferably reside on the electronegative atom in that compound. Okay, see this example. These two are the resonating structure of the same compound. So whether this is more preferred or this structure is more preferred, that is the question. These kind of questions may ask in entrance. So the negative charge is on the carbon, the terminal carbon, or negative charge on the electronegative oxygen. So the result will be resonance will favor this structure, and this is minor structure. So resonance will always favor the negative charge on the electronegative oxygen atom rather than less electronegative carbon atom. This is the fourth. The fifth rule of resonance, which says that resonance always preferred on compounds with no charge, like benzene. Benzene is neutral molecule, right? It's no charge is there. So it's always prefer a compound that are uncharged. If charge, resonance is possible in charged molecule or charged compound also. If charge, like charges means positive and positive charge, negative and negative charge on the same compound. Like charges should be as far as possible. The like charges, the distance between the same charge must be as far as possible. Okay, and unlike charges, a positive and negative charge on the same compound. Unlike charges should be closer as possible. This is the fifth rule. The sixth rule of resonance. This rule is used to identify the hybrid structure of the compound. So the rule states that more the number of covalent bonds in a resonance structure, resonating structure, more stable the structure is. Okay, let's consider the example. This is a conjugated system. A double bond, single bond, and again a double bond. Alternative pi bonds. Okay. So if these two are the resonating structure, okay. So this comes to here and this goes to here. So as a result of that, the first one obtained. A double bond comes between the middle two carbon atoms. So let's count the number of covalent bonds here. Sigma and pi. Okay. Here, the total number of sigma bonds 2 plus 1, 3, 4, 5, 6, 7, 8, and 9. Okay, 9. And pi bonds 1 and 2. So total will be 11. Okay, total number of covalent bond is 11. Okay, and what about these two cases? So if the electrons are moving to here, the first double bond is moved to shift to here, and as a result of that, a positive charge comes to one of the terminal carbon atom, and negative charge comes to another carbon atom, another terminal carbon atom. Or else, if suppose, what are we going to happen? This, the first double bond will move to here, and only the positive charge comes to the one of the middle carbon atom and negative charge on the second carbon atom. So let's count the covalent bonds here. In this case, sigma bond is 9. Okay, pi bond is 1. Total 10. In this case, sigma bond is 9. Pi bond is 1. Total is 10. Okay, so which structure is more stable? This one. The first structure is more stable, and these two are minor. So we can consider this as the hybrid structure of the resonance. That is the hybrid structure of the compound. Okay. So the sixth rule is used to determine the hybrid structure of a compound, which says that more the number of covalent bond in a resonating structure, more stable the structure is. So we can identify that structure as the hybrid structure of the compound. Okay. The seventh rule of resonance, the last and very important rule in the resonance, is all the resonating structure must have same number of paired and unpaired electrons. Let me repeat, all the resonating structure must have same number of unpaired and paired electrons. That means the sum of sigma bond, pi electrons or pi bond, and odd electrons, lone pair electrons must be same in all the resonating structure. That is very important. Okay, let's consider an example. See, the resonating structure of this conjugated system. This is a conjugated system, like organic compound, which is having conjugate system. Let's count the sigma, pi, lone pair, and odd electrons together. Okay. So the resonating, first we write the resonating structure. What will happen? First, this will move to here, and as a result of that, negative charge comes to the terminal carbon, and positive charge comes to here, and then this will move to there. The pi bond will again shifted to the single bond. As a result of that, one positive charge comes to the terminal carbon, and a double bond there, and a lone pair, a negative charge on the another terminal carbon. So let's count the paired and unpaired electrons in these three resonating structure. Let's see whether they are same or not. In the first case, the number of sigma bond is, how many sigma bond is there? 1, 2, 3, 4, 5, 6, 7, 8, 9. So in the first case, 9 sigma bond. Okay. So it's at 9 sigma bond. How many pi bonds are there? 1 and 2. 2 case. So here it is 9 and here it is 2. Okay. How many lone pairs are there? No lone pair. So 0. No odd electron. No free radical. 0. So total is 11. So the number of paired and unpaired electron, the first resonating structure is, total number is 11. Let's consider the second structure. Here, additionally, one lone pair is. So one lone pair is there. Number of sigma bonds, same 9, but pi bond is reduced to 1. Right? No odd electron. So resonating structure is 11, the same. So the third resonating structure, what will happen? The number of sigma bond is same, 9. Number of pi bond is only 1. And the number of lone pair is again 1. No free radical or odd electron. And the total number is 11. See? So we can identify whether the given resonating structure is following the resonance principle or not. We can, if in an MCQ question, four objects are given. Okay, 4 answers are given. Whether this is a resonating structure of this compound or not, we can identify using this. We can determine whether it is a resonating structure or not by using this rule. Okay, so let me repeat again. In all the resonating structure, the number of paired and unpaired electrons must be same. Or in other ways, the sum of sigma, pi, and odd electron and lone pair electron must be same in all the resonating structure. Okay, let's move to some misleading cases in resonance effect. Okay, so these are some examples comes in previous type entrance examinations. So whether resonance is possible in these 4 structures, let's consider the first one. Is resonance is possible? Yes, resonance is possible. Resonance is possible here because a positive charge, single bond, and a double bond. A positive charge in alternative position. So resonance is possible, and a positive charge will comes here, and this will comes here. Whether resonance is possible or not, that's the question. So in this case, resonance is possible. Okay, but the continuity is not there. So resonance is possible. These are misleading cases in resonance phenomena. Okay, and the second case in nitrogen, whether resonance is possible. Nitrogen is having 1 bond and 3 bonds. It's a quaternary ammonium. Suppose this bond comes here. What will be the valency of nitrogen? The valency will be pentavalent. Nitrogen will become pentavalent atom. That is not possible. So resonance is not possible in this case. Okay. Resonance is not possible. The reason is that when the pi electrons will move towards this bond between carbon and nitrogen, the nitrogen will become pentavalent. That is not possible. And what about this case? This is called aniline. A benzene ring which is connected with an amino group. This is called aniline. Yes, resonance is possible because this lone pair will comes here, this double bond will moves here, and a negative charge will comes there, and that negative charge will moves further, and this will comes here, this will comes here, and finally goes to there. So resonance is possible. Delocalization of pi electrons inside the ring is possible in this case. So resonance is possible. What about this case? In nitrogen, this is a kind of pyridine structure. What about this structure? This is not possible. Can you guess what is the reason? Because lone pair and pi bond not in alternative position. See, lone pair and pi bond not in alternative position. So we cannot consider this as resonance. Okay. So we move on to the fourth part. Types of resonance. So the resonance effect in organic chemistry can be divided into two parts. Positive resonance and negative resonance. This is mainly depends on the substituent group or the functional group attached to the actual compound. Okay. Let's consider an example. If this positive resonance, suppose this is a benzene ring, NH2. Nitrogen is carrying lone pair of electrons. What will going to happen? So nitrogen is this amino group is the substituent, right? So this lone pair will comes to here, and as a result of the delocalization will get started, and the double bond, the first pi bond inside the ring will goes to the terminal, and as a result of that, a double bond comes between NH2 and a positive charge here, a minus charge, and minus charge will comes here, and this will move here. The double bond comes here, comes here. This will move here, this will comes here. This will comes here, and this will goes here. And the hybrid structure will be right. So when a substituent group, amino group, is attached to a benzene ring, the substituent is carrying a lone pair of electrons or an odd electron. But what will going to happen? The lone pair will donate towards the benzene ring or an aromatic compound. Or the lone pairs are moving, the electron density is moving away from the substituent group. Such kind of resonance is called positive resonance. Okay. When the substituent group is having lone pair of electrons, positive resonance will happen. As a result of that, the electron density of the benzene ring or the aromatic group or the conjugate system will increases. Like this is aniline, like aniline, another compound is we can say OH. Which group is there? The oxygen is carrying lone pair of electrons, right? And X. What is X? Halogens. It can be Cl, fluorine, bromine, etc. So the substituent group is carrying lone pair of electrons, which will donate, displace the lone pair of electrons towards the conjugated system, which result in plus R effect or positive resonance effect. Now we move on to the negative resonance effect, minus R effect. Let's consider this example. Through example, we can define it. A benzene ring is carrying C double bond O. What is this? An aldehyde. Okay. An aldehyde group is there. Okay. So what will going to happen? This pi electrons will move to the oxygen atom. As a result of that, the pi bond inside the ring, the pi electrons from inside the benzene ring will move out. So as a result, there is a positive charge in the ring, double bond C, H, and O minus. Again, this will move here. H. This will move here. This is here, and this bond will come here. So as a result of that, we have arrived at the initial structure. So when a double bond, is present in the substituent group, remember that case. When a double bond is present in the substituent group, what is happened? The pi electrons from the ring move outside. That is, the substituent group withdraw electrons density from the benzene ring. This kind of effect is known as negative resonance effect. If the substituent withdraw electron density from the benzene ring or it pull the electrons from the benzene ring, it is called negative resonance effect. There are certain examples like NO2. If NO2, nitrobenzene, nitro group comes in the position of aldehyde, the same effect, negative resonance effect facilitated. Or C double bond O H, this is aldehyde group that we have illustrated here. Or C double bond O keto group, if it is R and this is attached to here keto group. Or C double bond O OH, an acid group, etc. So a nitro group, aldehyde group, keto group, acid group. What is the specialty there? A double bond is there. That is the trick. Double bond is there. If a double bond is carried by the substituent group, there is a chance of effective negative resonance is possible. If lone pair is there, there is a chance of happening positive resonance. Okay. So remember, these are the two types of resonance effects. Okay.